Okay. Another plot that we're going to use in order to visualize our data and try and identify its features, and something that gives us more information than what we saw in the time plot, what we call seasonal plots. Let's start with an example using the cost variable in the A10 table, which we defined in the previous section of the book. So if you need to, please have a look at the previous section of the book to remind yourself what this table contains and what the cost variable is. A general feature of the time plot that we see for the cost variable of the anti-diabetic drug sales is an increase in the trend. So there's an increasing trend. There's strong seasonality, and the seasonality increases as the time series increases in level as well. Now let's have a look at the seasonal plot. Let's first explain what a seasonal plot is. So a seasonal plot is a plot where the observations are plotted against the month at which, not the season at which they are observed. Here the season is month. So basically when we look at these lines, it's the same plot that we saw before, but years are plotted on top of each other. Basically the data wraps around per year. So a couple of features that we can identify by looking at the seasonal plot. We can see and we can confirm that when we looked at the previous graph, we identified points which led us to believe that January was the peak season for anti-diabetic drug sales. And this is confirmed here where the spike is in January. Okay. Then another feature that we see here is that there's a drop in February since the spike is in January, but then there's an increase between February and March. There seems to be always a jump. Now that is artificially caused because there's 31 days in March compared to the 28 in February. So usually with seasonal data, we will see that change. And as the months go between 30 and 31, there might be a little bit of variation. The variation is more obvious between February and March. The other feature that we see here is that the years seem to be here in ascending order, and that's the case because we have trend in the data. So 1992 is higher than 1991, 93 higher than 92, and so on. Both these features, or the features that I just spoke about, we could identify in the time plot. What we couldn't identify in the time plot is some unusual observations. For example, this March 2008 observation seems to be considerably lower than February 2008 and not adhering to the patterns that we've seen up to there. So something weird has happened in this observation. The other thing we can see is that the 2008 observation, the June observation of 2008, seems to be much lower than the 2007 June observation and much lower than the May 2008 observation. Hence, maybe incomplete data or something has happened there. So if we were forecasting and projecting forward, we need to make sure that we know that or account for that. Okay, so in seasonal plots, data plotted against the individual seasons in which the data were observed. So in this case, as I said in the previous slide, a season is a month. Something like a time plot, except that the data from each season are overlapped. Seasonal plots enable us to identify the seasonal pattern more clearly. If you had any doubt before, this can be verified, but it also allows us to see any substantial departures from the usual seasonal pattern that we see, hence the unusual observations that we identified before. Okay, and here's the function that we've just used, and I've showed you how to use. Let's have a look at another example. We're going to use the Oz production table, and from here we're going to extract beer. This is the beer production in Australia. We're going to plot this using a time plot. So this is quarterly data of Australian beer production in megalitres. So by observing the time plot, again, we can see we have a highly seasonal data, but without thinking clearly or without trying to focus in some feature of the data, we don't know when this spike happens. If you carefully look at it, I think, yeah, let's move on to the next slide where I'm plotting the point on top of the line. So you can see, let's go to this 2005 Q1. So this is Q1, Q2, Q3, Q4. Q1, Q2, Q3, Q4. So the spike in beer production in Australia happened in Q4. Now, Q4 contains the beginning of summer, hence production then increases getting ready for the summer period. Okay. Another general feature that you might see from the time plot is that there's a general downward trend we can see. Okay, let's move on to the seasonal plot and see if we can observe anything useful here. Well, clearly now we can see when the spike happens. Clearly the spike happens in Q4. Q2 is lower than Q1. Q3 is a little bit higher. So Q2 in Australia is the winter quarter. So production in the winter quarter is low. And as we're getting into the summer quarter, production gets increases so we can be ready for summer. I guess an unusual observation is this 2004 quarter, which is lower than everything else. So here, the downward trend, you can sort of see the years maybe in a descending order, 1992, 93, 2002, 2000, 2007. So a little bit of a downward trend. But this is 2004's spike is out of order. This peak is out of order. So if we go back to the previous slide, you can see that 2004 Q4 is down here. So something has happened in that 2000 Q4, which signals some unusual pattern in the seasonal pattern. Okay, let's have a look at another example. And as we are moving now to half-hourly data, this gets even more interesting. Okay, so let's talk about the data first. This is Victorian electricity demand. It's demand observed every 30 minutes, so it's half-hourly data. The data's got a timestamp on it. It's observed in Australia, Melbourne. It's Victorian data, but the timestamp on it is in Melbourne in Australia. The table has got 4 columns. So the first one is a timestamp itself. The second one is demand, and I believe this is megawatts. Then we have a temperature variable. So this is degrees Celsius, observed in Melbourne in some Bureau of Meteorology station. Then we have a date variable. This sort of overlaps the time. You can either use a date variable as in the day, or you can use a timestamp variable as in a specific timestamp of the day. And then we have a dummy variable, which signals holiday or not. So the first 2012 is a holiday anywhere in the world. So this variable here is true. Okay. So let's have a look at a time plot of this data. So the data goes from 2012 to 2015, and there's a lot of observations here, a lot of half-hourly observations. So if you look at our table, the table has 52,608 rows. Hence, there's a lot of sort of blue ink on our graph. But there are some features we can see here, and we can discuss them here. But since we're talking about season plots, let's move to the next graph and discuss the features that we see there. So by default, well, with half-hourly data, there's multiple seasonality that takes place. So we have the time of the year, and by default, when I use GG seasonal plot, if I don't tell it anything else, if I use GG season, if I don't tell it anything else, it will plot the time of the year. And then we have time of the week, and also we have time of day. Okay, and we'll see those in the next couple of slides. So these are years plotted on top of each other. Okay, we have 2012, 2013, 2014. So let's observe some features using this seasonal plot. So January, February, and December are summer months in Australia. Hence, we see a lot of variation and a lot of spikes in demand, very hot days, and a lot of air conditioning happening. So hence, we see this increased variation in summer. Then as we're moving across our x-axis, we have our autumn, which is sort of lower demand than summer, but then we have higher demand in the winter months, June, July, August. Then we have spring, which is a fairly stable season in Victoria. So hence, lower demand than winter months and summer months, and fairly stable. The variation there is fairly stable. Now, if we go back to our time plot, we could probably see that all those features in this time plot. So here's the first summer of 2012, a lot of variation. Here's the winter, then 2013 summer, here's the winter, 2014 summer, and here's the winter of 2014. Okay. So this first season plot hasn't shown us a lot more information than what we could have seen in the time plot. Let's move on to our next season plot and now look at, so now let's look at time of the week. Okay, so we have 7 days in the week. We have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday in the weekend. So the first thing that should jump out to us is that the weekend demand is lower than the weekday demand. Okay, we see that there's the seasonal pattern in the weekends is also different from the seasonal pattern on weekdays. So there's a couple of spikes on the weekends, but the first spike is lower than the second spike, especially for Sunday. The first spike is lower than the second spike. So this is the morning spike and the evening spike, if you like. In the weekdays, these spikes are sort of equal in the height and the demand of electricity. Hence, if we were modeling this, we would have to account for different seasonal patterns in which day of the week we are actually capturing. So the next seasonal pattern that we're going to see, the next seasonal plot we're going to see is time of the day. So on our x-axis here, we have 00, which is midnight. Then as we're moving along, here is the lowest demand that we see in a 24-hour period. Okay, so this is 4 a.m. People are sleeping, not a much demand. And then as we're moving 6 onwards, people are waking up, hence demand increases. People go to work, hence demand sort of decreases a little bit, and then comes 5 o'clock, 6 o'clock p.m., people return home, hence another increase in demand. As we're moving through the evening, demand decreases, and then maybe just before we go to bed, there's hot water services, or I'm not exactly sure what happens there, but there's a little bit of increase in demand. And then we see some very, very hot days where the patterns are completely crazy, where you see a lot of high spikes. There's a couple of sort of weird stuff happening down here, and that is because of daylight savings. So there's days where the clock changes back. So in these 3 days, there's a couple of extra observations, a couple of 30-minute periods observed, okay, for each of the years that we're looking at. And there's also shorter days going the other way, but you cannot see them here because there's so much happening there. So these features in this GG season for daily or time of the day, and these features for time of the week, you could not see from this plot or from the time plot.